All right, so what I want to do now is start chapter 4, and like the book, now is a good time to basically go through the basics of finite dimensional normed vector spaces. We're just like the book, we're only going to basically cover the basic properties because particularly looking at quantitative relationships between finite dimensional normed vector spaces is a huge challenging subject with particular relevance to applied math and data science, since most real-life data is very complex and high dimensional. Okay, so just a definition. Let's say I have a normed vector space X. Let's say I have two norms on X. X could be just a normed vector space in general, not necessarily complete or finite dimensional. We say that these norms are equivalent distinguish between a U and a V if there exists two constants positive where kind of the obvious is true. And I probably did this definition already at one point, but it's all right. Basically, you have convergence in one norm if and only convergence in the other norm. And that's basically quantified. I mean, that's basically what this says, essentially. Okay. This is actually a little stronger, that up to a constant, these norms are kind of the same. Up to two constants, really, little m and big M. Okay. This is true for any x and big X. Okay, so let's prove the following proposition. If you haven't seen this before, it kind of looks magical, but it's really not. It's not nearly maybe as deep as it would look. Any two norms, say 1, 2, on a finite dimensional normed vector space X, meaning it's a normed space that has a finite basis, finite homobasis. So finite dimensional in the usual linear algebra sense. These are equivalent. So we're not going to get really all that practically useful bounds here. We're just going to get fairly abstract bounds, but that's enough for what we're doing. Like I said, we're not very quantitatively looking at how finite dimensional normed vector spaces are related to each other. In the first place, that really requires a lot of probability theory that we've obviously not touched. We haven't done any probability theory in this course. But anyway, so what's the proof? The proof is fairly straightforward. The depth is really the Bolzano-Weierstrass theorem. So let's just say we have a basis, a homobasis. So let's say it's a basis for X, and we can define a very natural norm. You can check this as a norm. It's pretty trivial. The infinity norm, defined in the following way. Where here the alpha I are just the coefficients of X with respect to the basis E1 through En. Of course, because this is a basis, this is, if every x is written uniquely in this way, so there's no ambiguity here. And like I said, you can check that this is a norm, right? So it's enough to show that this norm here, the infinity norm, with respect to this orthonormal basis, and any norm on x are equivalent. Equivalency of norms is obviously a equivalence relation. There's really not much there. So in particular, if I have norm 1 is equivalent to the infinity norm, and the infinity norm is equivalent to norm 2, then norm 1 and norm 2 are equivalent. Right? So this is my task. And one direction is really not too much, not too hard. The other one's a little trickier. So first, if x equals this sum here, then I can just use the triangle inequality. So I'm just using this here. By a triangle inequality, this is less than or equal to, I'll pull out the alpha I and take the norm of EI. Okay. Well, I can pull out the maximum of the alpha i's. So this is less than or equal to, well, that's exactly what the x norm is. The x norm is the max of these, So this sum doesn't go anywhere. But there's finitely many of these. I mean, certainly if x is infinite dimensional, you can always do this, but you have an infinite sum, or, yeah, I mean, you, yeah, I mean, you wouldn't be able to do this uniformly in all x if x has infinite dimensions. The point here is that n works for every x whatsoever. Okay? We're saying, so maybe to make this absolutely crystal clear, in the standard linear algebra sense, we're saying n is a dimension of my finite dimensional vector space. So this is going to be equal to, well, let's call this constant m. It's completely independent of x. So we get 1/2 of our result, the easy half. And again, you can, up to here, you can do this for an infinite dimensional normed vector space. But this m here most certainly depends on x, and that's no good. That's not what we want. Okay. In this definition here of equivalence, we have little m and big M independent of x. This works for all x. Okay. So let's do the other direction. This is, admittedly, this is a bit clever. If I was given this as a homework, I would probably have to really think hard on doing this. It's not trivial, but it's not too difficult. All right, so let's say D is the following infimum. Obviously, 0 is a lower bound for this set here. So the infimum exists. This could be 0. we want to prove that it's not 0. So it's enough to show that D is positive. Why is that? Well, if x is not equal to 0, then pick any x whatsoever and divide by the infinity norm. So certainly this here has infinity norm 1. What I'm circling here has infinity norm 1. So this is going to be, well, it's bigger or equal to the infimum. That's, the infimum is a lower bound. So this is bigger or equal to D, which is positive. So this means that the norm of x is bigger or equal to D norm, the infinity norm. We proved the other half here, the norm of x is less than or equal to big M times the infinity norm of x. Here we get the other direction. Rather, the infinity norm is less than or equal to 1 over D times the norm of x, in my original norm, whatever it is. So yeah, here norm of x is less than or equal to a constant times the infinity norm. Here the infinity norm is less than or equal to a constant. That's actually not infinity, because D is positive times this. All right, so, right, that's our task. So let's perform that task. Okay, so, right, so we don't know what D is. That's okay. We're going to prove that it is, we're going to directly actually prove that it is not 0. Whatever it is, we can sure as hell pick, and I'll use the book's notation, we can pick yk in big X with norm, infinity norm 1, where this converges to D. I'm just, this is infimum. You can always pick stuff in this set converging to the infimum. Nothing much there. Okay. Right, so now kind of the key point here is that the infinity norm is kind of special, as we'll see. So let's write yk as I equals 1 to n. Just write it out in terms of this orthonorm. There's no inner product here. This orthogonal base. This basis here. There is no orthogonality. There's no inner product. Sorry about that. Yeah. So for each k, we have these constants alpha, k, I. That's all we're saying. Okay. However, for each k, well, this is going to be equal to the infinity norm by definition. 1 second. Right. And yeah, this is going to be equal to 1. Okay. So in particular, yeah, this is for any natural number k. So yeah, so for all k and all I between 1 and n, integers I between 1 and n, this is a bounded sequence. So I can use the Bolzano-Weierstrass theorem. So basically, you can, another way of thinking about it is alpha ki as I goes from 1 to n, or it's just alpha k is a bounded sequence in Cn. So let's say alpha k is so this is obviously bounded. Okay. So by the Bolzano-Weierstrass theorem, or just really apply Bolzano-Weierstrass theorem to each term, basically same thing. So you can pick a subsequence converging to, maybe this is not the best notation. So, well, whatever. Yeah, maybe that's a little better. Right, so for each k, yeah. Yeah, so yeah, we have convergence to, let's say, alpha I and C for each I between 1 and n, integer I between 1 and n. Okay, well, ykm is a subsequence of yk. So we still have convergence in the original norm, whatever it is, to D. Again, that's how we picked yk. It converges to D. So any subsequence converges to D. Well, let's say, using the book's notation, y0. So the book uses, I think, bi for the basis. I like ei because we're familiar with ei from linear algebra. So whatever. Yeah, so define y0 in the obvious way. Just alpha I ei. Well, what then is ykm minus y0 in the infinity norm? Well, this here is just going to be alpha km I minus alpha I. So by definition, this is going to be equal to just well, this max here. Well, for each, yeah, so we have this as true for each I. Oops, didn't want to do that. So this is true for each I. That's what we are assuming. Right, so, right, if this is true for each I, then obviously this max here, I should say, I don't think there's any confusion, but this is as m goes to infinity. Yeah, so this maximum here is going to converge as m goes to infinity to 0. Okay. Okay, but what does that mean? Well, we just proved before that well, anything in this norm here, whatever the hell it is, we don't know what it is exactly, we don't really care. It's less than or equal to m, big M, where big M, remember, is this here. So this norm is less than or equal to big M times the infinity norm. So it's M, infinity norm, converges to 0 as M goes to 0. Well, we know in general by the triangle inequality for norms that no matter what norm we have, norms are continuous. So that, in the sense that d is ykm is going to be, well, if ykm converges to y0 in this norm, then the norms converge. Right? Right. So, right. So how does this help us? Well, let's see. Did I do this here? No. All right. So, so also we have convergence in the infinity norm. So we have, well, convergence in this sense just from this here. Well, remember what this is. This is just 1. We're assuming all these have norm 1. So thanks to what I am writing, this equals 1. And why does this help me? Well, this is it. We're done. In particular, this is a norm. The norm of this is not 0. We don't really care all that much that it's 1. We care that it's not 0. All right? Because that means D is the norm of 0 is not 0 because this is a norm. The norm is not 0 if y is not 0. Y0 is not 0. So we just proved that D is not 0. All right, so let me continue on with a few straightforward propositions. And then we'll dive into compact operators, which is really the main point of chapter 4. Okay, so we have the following proposition. Basically, this result here is really the main basic property of normed vector spaces. Any two norms on a finite dimensional normed vector space are equivalent. So let's say I have two finite dimensional normed vector spaces. So let's say, in particular, in the usual linear algebra sense, so both x and y have finite Hamel bases, there's finite regular vector space basis, and the dimensions are the same. And that's both finite. Right. So if this is true, then we have that these two norm vector spaces, let's just say this is any norm on X. And let's say this is any norm on Y. This is isomorphic. They're practically the same space. In what sense? In the sense that there exists bijective linear X to Y where, well, you can probably guess where this is going, where basically it's kind of like the norms on X and Y are basically the same. And this is true for all X and big X. Okay, so again, isomorphisms in this context, two isomorphic spaces, normed vector spaces in this context is an equivalence relation. Two normed vector spaces being isomorphic in this sense is a equivalence relation. So if I can prove that any normed vector space X is isomorphic to Cn with the infinity norm, then I'm done, because then Y is isomorphic to Cn with the infinity norm, and hence X and Y are isomorphic. Okay. So first of all, let's say n is a dimension of X. And yeah, as I said, without loss of generality, let's just say this is Cn with the L infinity norm. Well, you know what the L infinity norm is. It's just the same infinity norm that we had before. So maybe I'll just, yeah, this is, no need to put L there. Yeah, it's just a standard infinity norm with respect to the, well, just a standard L infinity norm. Obviously here Z is 1, with all of these being complex. I should say the same thing is true if we're dealing with a real vector space, we do the same thing for Rn. Okay, well, actually, I do want to distinguish. So let's do, we will do, right, L infinity. Do want the infinity norm to be reserved for something else in a moment. So by the previous theorem, previous proposition, this norm here on X is equivalent to, well, every norm on big X. Right. Okay, so, and the infinity norm here is just exactly what we described before. We fix a basis, just fix a basis and define the norm in this way. That's all we're doing with respect to this fixed basis. We don't care what basis it is, just fix one of them, and that's that. Okay. Yeah, so I guess I'll just write that down because I'm going to have to write down X in terms of the basis. So just kind of remind you. Here, X is written in this basis. Right, so we define this map here in kind of the obvious way. Well, let's just say this is alpha 1, alpha n, which obviously in Cn. Right, so we're basically done. Well, obviously, by definition, this is an isometry from Cn L infinity to X, the infinity norm on X, just previously defined. Okay, so what does this mean? This means exactly what we wanted to prove. So this here is less than or equal to the infinity norm. Well, this also equals the infinity norm. Okay. Right, so we're done. Every finite dimensional normed vector space of dimension n is isomorphic to Cn with respect to this L infinity norm, which is, well, Cn with the L infinity norm is we proved abstractly. It's equivalent to Cn with the standard L2 norm. You can check that absolutely trivially directly, but it's just the infinity norm for these purposes is a little easier for us to deal with. Okay, so a few corollaries. First, any finite dimensional normed vector space X is complete. And in particular, any finite dimensional subspace of a normed vector space is closed. So the second sentence just follows from the first one. If we have a finite dimensional subspace, then it's complete and hence it's closed. Not much to say about that. All right, so what is the proof? Well, the proof is pretty straightforward. Kind of trivial at this point, but make sure everyone's on the same page. So let's say we have a Cauchy sequence in big X with whatever norm big X has. Then defining psi as we did in the previous previous proposition, this is Cauchy. Cn. That implies psi xn converges to some z, which we write as psi of x, where here just psi of x is just going to be the inverse image of z. Again, we were, go back and unravel this. Everything is very explicit. In terms of some abstract basis that we don't care what it is, we just care that we're dealing with a finite dimensional vector space. And I should say here, not that it matters, but this is a dimension of X. So that's what n is. And obvious, but right. Okay. Yeah, so finally, xn minus x and the norm big X. Just use linearity. This is going to be less than or equal to let's say 1 over little m. So by linearity, this is xn minus x. Right. Well, I haven't used linearity yet. Sorry about that. So this is going to be equal to little m psi xn minus psi of x. And that converges to 0. All right, so I need 2 more propositions that I'll get through very quickly. First, if I have a linear map from any 2 finite dimensional norm vector spaces, then this has to be bounded. There's not much to this. Implies T is bounded. Proof, really not a whole lot to this. If the norm of x equals 1, and again, let's write let's write x in terms of my basis E1 through En. Let's say x. Actually, so we don't even need, we do not need y to be a finite dimensional vector space. We just need x to be a finite dimensional vector space. So Tx is going to be T I equals 1 to N alpha I EI. So you're kind of doing the obvious thing. triangle inequality. But at the very least, t is linear and it spits out stuff in y. So nothing here is infinite. Okay. Well, this is obviously less than or equal to the infinity norm n times the infinity norm of x times the maximum ti. Okay, this is finite. So this is less than or equal to, using notation, let's say this is, I don't know, big N. This is going to be less than or equal to N. This, not that it matters, but using notation from before, we said this is less than or equal to 1 over d times the norm of x. And that takes care of it. Right, and last but not least, we have the following corollary. Let's say we have t from one normed vector space to another. It's linear. Let's assume that the range of t is finite dimensional. In other words, we have that t is finite rank. That's what we, if the range of t is finite dimensional vector space, then we say that t is of finite rank. And we've looked at we characterized finite rank operators on Hilbert space, on a separable Hilbert space in one of maybe the second homework. So should be, it shouldn't be too strange of a concept. Okay, so I claim that if xn is a bounded sequence, then there exists a subsequence x and k where t, x, and k converges in y. As we'll see in the next, or in a moment, any such operator is called compact. By definition, I'll make that definition exactly precise in a moment. Yeah, so we're basically proving that any finite rank operator is compact. Proof is really not too bad. Let's say txn is in the range of t. So if we have the same map that we had before, where here n is the dimension of the range of t, then, right, so this is bounded. T is a bounded operator. Yeah, so sorry, I should include that T is bounded. So yeah, I do need to include T is bounded. Right, so yeah, this is a bound, because T is bounded, this is bounded in Cn. So we have a, by Bolzano-Weierstrass stress theorem, we can pick a convergence subsequence. This converges in C, implies that Txn K converges in, well, in particular, converges in the range of T. Okay? And in particular, it converges to something. We really don't even care that it converges to something in the range of T. We just really care that it converges in Y. Okay, so yeah, next up, we're going to put this to good use. In particular, we're going to use, maybe I don't know if it's in this video or the next one, but we're going to put this corollary to good use in discussing compact operators on a separable Hilbert space. All right, so what's a compact operator? Well, a compact operator is defined like the book does as follows. So the definition of a compact operator, let's say I have T linear from one normed vector space to another. So by definition, T is compact. We say T is compact if there's a kind of Bolzano-Weierstrass theorem thing going on. Xn bounded implies Txn has a convergent subsequence. Okay, so a very easy proposition using the fact that compactness and sequential compactness are equivalent in metric spaces is that, 1 second, is that T, by our definition, compact, is equivalent to the closure of T applied to A is compact in Y. These little bars here, make sure we're all on the same page. Well, here A is a bounded subset . And this here is a closure in Y. So we know compact subsets have to be closed. So the image might not be compact. It's pre-compact. Any bounded sequence or any, if A is bounded, any sequence in the image of A will have a convergent subsequence. It just might not converge to something in the range. That's rather special. But it will certainly converge to something in the closure of the range by definition. So yeah, very easy little exercise, not much to prove. again, just using the fact that in a metric space, compactness is equivalent to sequential compactness. Right? So yeah, both like normal, regular compactness and sequential compactness kind of definitions of T compact. Kind of normal compactness, by that I mean basically this here. Both of them are going to be very useful, as we'll see in a moment. So both of these equivalent, basically, definitions, what's in the blue and what's in the yellow, are both very useful. Okay. All right, so a very easy proposition is the following. Maybe not super intuitive, but it's very easy to prove. T compact implies T bounded. What's the proof? Well, prove the contrapositive. If not, then obviously by definition, the supremum is infinity. So by definition, there exists xn and big X with each norm 1 and txn, let's say, is bigger or equal to n. Well, this obviously implies that no subsequence of txn converges. Well, any subsequence is going to be unbounded, so any subsequence is going to have to diverge. Any convergent sequence is bounded, so no subsequence txn converges. Well, xn is bounded. I mean, it's norm 1 each. So by definition, that says T isn't compact. All right, so yeah, a simple example would be through a very easy example. So let's look at the forward shift that we've seen many times before. Let's say S takes L2 to L2. We'll take something x1, x2, et cetera, and little L2. Well, remember, this just shifts everything over kind of one spot. Okay. So I claim that this is not compact. Otherwise, it's about as nice of an operator as you could ever want. It's, I mean, I guess it's not invertible, but still, it's bounded. It's a bounded isometry, so otherwise, it's a pretty damn nice operator. But it's not compact, and that's very easy to see. Yeah, so as usual, let's say En is the nth canonical kind of basis element. So this is the nth spot here. All right, put that over here. Yeah, so pretty trivially, we have SEN just shifts everything over 1. Well, if you have everything as 0 except 1 in the nth spot, if you shift everything over 1 spot, you get all zeros except 1 in the n plus 1 spot. Okay. Yeah, so I claim this has no convergent subsequence. Well, let's take an arbitrary subsequence. And let's check that it's not Cauchy. Let's call it E N K. Take this squared. Well, this is just EN K plus 1. This is E and M plus 1. Well, just by Pythagorean's theorem, if K is not equal to N, and again, I'm just picking an arbitrary subsequence of SEN, call it SENK. So let's say K is not equal to M. So by Pythagorean's theorem, this is, well, it's just the norm of this squared. Norm of this squared is 2. So, yeah, that implies that this is not Cauchy. Right. So that takes care of the proof. Not a very deep result, but a nice, easy example. Okay, on the other hand, this is in stark contrast to situation. I should say, of course, just want to make something clear. Yeah. So S obviously is linear. That's not in doubt. So yeah, this example is in stark contrast to the finite dimensional situation, or particularly the CN situation. So if T from Cn to Cn is linear, I claim T is compact. Well, one of our propositions is that T is bounded. So Xn bounded obviously implies T Xn. Sorry about that. Well, this is a subset of Cn. So by Bolzano-Weierstrass theorem, this has a convergent subsequence, and hence so T is compact. Right. So yeah, and this also works for really, if you think about it, it works for any finite dimensional vector space, particularly Bolzano-Weierstrass theorem holds in any finite dimensional vector space. I'll leave that for a very easy exercise if you so desire to try that. Again, the depth there is that you have a finite Hamel basis. And so you can basically, with respect to that finite Hamel basis, apply Bolzano-Weierstrass theorem, essentially. Okay, right. So let me state a very useful but very elementary proposition, and then we'll prove something very useful and rather deep. Maybe it's not super deep, but it's highly non-trivial and extremely useful in practice. So let's say S is bounded on a normed vector space X. T1, T2 is compact. So this is kind of saying that compact operators form a two-sided ideal in the vector space, or really the algebra of bounded operators on a normed vector space. So this is a really kind of interesting kind of algebraic property that, So we haven't really talked all that much about algebraic properties like this. I would do that in a second semester. If there's interest in me teaching that, certainly let Professor Kwan know. We would talk about Banach algebras, Banach spaces that are algebras, and C-star algebras in a second semester. Or you could just look in the book. It's the next chapter, I think, chapter 5 and 6. Anyway, so 1, linear combinations. Let's say both of these are compact. Linear combinations of compact operators are compact. I'm assuming we have a vector space over the complex numbers, also works over the reals. But yeah, the ideal property is that, it's a two-sided ideal. So ST1 and T1S are compact. All right, so what is the proof? 1, I'm not going to bother. It's really nothing to it. 2, let's say Xn is bounded. Really, it's just the definition of, it's really just boundedness is equivalent to continuity. So let's say T1Xn converges. So let's say it converges to Y and X. Okay. Well, by continuity, this converges obviously to SY. Right. Well, by definition, that means this is compact. We start off with Xn bounded. ST1 applied to Xn. Has a convergent subsequence. So the other part is just as easy. So similarly, xn bounded implies that Sxn, like the fact that Sxn is sorry, the fact that S is bounded means that Sxn is bounded. That means, well, just by compactness of T, compactness of T1, that means that T1S applied to Xn has a convergent subsequence. And that's it. Really not much to that. All right, so yeah, let's get to the following. Let's prove the following useful theorem. And this is actually surprisingly useful in practice. If you want to prove an operator is compact, this is kind of your go-to way of doing it. This is really one of the most useful and easy ways. I shouldn't say easy because it's not easy to apply this, but this is really how you often just apply how you prove things are compact. So if X is a Banach space and I have a sequence of bounded operators on X that are compact, then Tn converges to T and the operator norm being a little redundant here, but it's all right. This implies that T itself is compact. Okay. All right, so what's the proof? Well, the proof isn't too hard. It's the diagonalization procedure, kind of like we did for Banach-Leoglu. It's actually very similar to the proof of the Banach-Leoglu theorem. All right, so right. I should mention I've used this result in my research. In particular, there's a lot of research going on these days on compactness of Toeplitz operators on various holomorphic function spaces. You know, if you have a reproducing kernel Hilbert space of holomorphic functions, you have an orthogonal projection, and hence you have a Toeplitz operator. You can always ask the question, when is this Toeplitz operator compact? And often what you want to do is cook up, to prove a Toeplitz operator is compact, you cook up other compact operators, other operators that you know are compact, usually by Montel's theorem, if you remember that from complex analysis. And then you show that you have norm convergence. So, so let's say Xn is bounded. Yeah, if this sounds intriguing to you, definitely I'd be happy to talk to you more about compact Toeplitz operators. There's still a lot of research to be done on that, on those rather. Um, okay, so let's say xn be bounded, and I'm going to use the book's notation rather than the previous notation for the Banach glue theorem. Right. So the problem, or maybe I shouldn't say problem, the kind of issue is that we have all these different compact operators. So, we have all these different convergent subsequences, like Ti applied to Xn has a convergent subsequence, but that's going to be possibly different for each I. So how do we handle infinitely many different subsequences? Well, we perform a diagonal argument. That's exactly what the diagonal argument handles. Okay, so let's start with T1. T1 is compact. So let's say we pick a convergent subsequence, which I'll call x1n, where T1 x1n converges. T1 is compact, so I can do that. So this is a subsequence of xn. So if you want, maybe you can call xn kind of x0n, if that helps. But okay. Okay. So 1 second. Sorry about that. Okay, well, kind of trivially, we have, and just to emphasize, let me maybe put ends here. Okay, well, this is it's a subsequence of a bounded sequence, so obviously this is bounded. So T2 is compact, so apply T2 to this subsequence and pick a further subsequence, which we label x2n. Right. So again, just to emphasize, this is a subsequence. I should do sub SUB SEQ. The subsequence of x1n right. Maybe let is not the right word. Let's say assume this converges by compactness. We can always pick subsequence where this converges. Right. And just keep going and going and going. Continuing. So inductively, if we have, let's say, xk minus 1n, we can pick a subsequence make that clear. So pick a subsequence, let's say for k, k bigger equal to 3. We did k equals 1 and 2 already. And again, to emphasize, I'm going to let write n equals 1 to infinity. So pick a subsequence xk of xk minus 1 n. So obviously a subsequence of my original sequence. Maybe let's do one more to emphasize this. So this one here, we picked as a subsequence xk minus 2. Well, we pick it where t, k, x, k, n converges. All right, so yeah, I'll just quickly draw kind of the diagonal picture. I mean, it's very, like I said, it's basically the same picture, same idea, a very similar idea to what we did for Banach-Aleoglu in the separable case, separable Banach space. Right, so keep going. Right, so yeah, so this is a subsequence x. This whole, all these are a subsequence of this. All these here are a subsequence of this. Well, each one, let's say x1. Obviously, each one here. This is a subsequence of my original sequence. All right, so what do? Green. I pick the diagonal. And what am I going to do with the diagonal? Well, I claim that t xn n converges. Okay. So first, I want to emphasize that xn n is a subsequence of my original sequence. It might be obvious. That's obvious. That's great. If not, then let me kind of make that clear. I mean, if you do remember, we basically proved that when we did Banach-Aleoglu theorem, but anyway. Yeah, so first, well, so, I mean, the fact that it's a subsequence is kind of trivial. You know, this row here is a subsequence of x1, x2, x3. This row here is a subsequence of x1, x2, x3. The third row is a subsequence of a subsequence of a subsequence, subsequence of a subsequence of x1, x2, x3. So when we go along the diagonal, we're just getting pushed farther and farther along my original sequence. So this is pretty plainly a subsequence. Okay. On the other hand, so xn subsequence of xn, and if k is bigger than j, then xkn n equals 1 to infinity is a subsequence of xj n equals 1 to infinity. Right? Just because, we're, the go from the k row to the j row, we just take k minus j subsequences of the sequence xjn as n goes from 1 to infinity. So yeah, it's a subsequence. Okay, so that means, by basically definition of a subsequence, xkn equals xj. Let's call this mn for some m n bigger or equal to n. So actually, k is bigger than j. Sorry. Yeah, that's fine. So in particular, if n is bigger than j, then xnn is going to be xj mn for some m n bigger or equal to n. So what does this tell me? This tells me that right, this tells me that this limit here, tjxn, is going to converge. Why? Well, xnn is, I can write it as tj is tj, so it's xj mn. Okay. And we picked precisely each of these in such a way that this converges. Okay. So in particular, tj xjn converges. Mn is bigger or equal to n. So as n goes to infinity, this is going to converge. And again, this is nothing more than the fact that this here converges. Okay, so let's say M is the supremum of all the norms of xn's. Okay. We're assuming xn is a bounded sequence, so this is certainly finite. So let's now check that Txn is Cauchy. That'll imply that it's convergent, and that'll finish up the proof. So Txn xn minus Tx m xm. So first of all, let's say we have some fixed little j, and n and m are bigger than j. I'll specify what j is in a moment. And let's just say these are just two natural numbers. Whatever. Okay, so do the triangle inequality in a not terribly subtle way. So it's going to be Txn n minus T j xn n tjxn n minus tjxm m. So the basic idea is that I want to exploit that that tjxn xn converges for fixed n as n goes to infinity. Again, just because of this fact here. Okay. All right. And then I want to judiciously pick j. I'll do that in a moment. Judiciously pick and fix j. Okay, so this is going to be, we have last but not least, tjxm m minus txm m. Okay. Well, for both of these here, I can just basically factor out a t minus tj. So this is really going to be t minus tj applied to xn. This is same thing, going to be t minus, or tj minus t applied to xm. Okay. So this is less than or equal to, well, 2 times big M, the norm of x, the norm of the soup of the norms of all these elements here. Remembering xnn and xmm, they're subsequences of my original sequence, minus the operator norm t minus tj, right? And, well, this term just doesn't go anywhere. Let's call it, I don't know, star here. Or let's, let's call this star here. Okay. All right, so what do I do? Well, if I want to prove that this is Cauchy, I need to pick epsilon. So pick j where t minus tj, an operator norm, is less than epsilon over, let's do 4m. So this gives me that txn and txm is less than or equal to, well, epsilon over 2 plus this star term here, which I'll just write, So the point here is that we've now reduced the situation to basically fixing once and for all for this epsilon, j. Obviously, j depends on epsilon, but that's all right. There's no problem there. Right, and what does this mean? For this fixed j, pick big N, where this term here is less than epsilon over 2. Remember, we showed using this diagonal procedure that tj, xn, xn as a sequence converges for each, particularly for n bigger than j. Well, okay, pick n. Let's say, just to make sure, so we do need this, so that's fine. So let's say n is bigger than j. So j depends on epsilon, n is going to depend on j, which depends on epsilon. So everything just depends on epsilon. No issue there. So tj xm. Right. So yeah, just right. J just depends on epsilon. We're picking j where this is true. I mean, it depends on the supremum of these xn's, but that doesn't matter. But yeah, this depends on epsilon. So big N depends on epsilon. Right. Okay, so that finally says that this is less than epsilon over 2 plus epsilon over 2, which is epsilon. It's really less than, but whatever. And that takes care of the proof. That proves that as a sequence, this sequence here is Cauchy.